All right, so part two here. Once we've kind of got the idea down about those Riemann sums, how to add up those little tiny areas to make up the full area for a decent approximation, we get to this thing called the fundamental theorem of calculus. Now, this is technically in section 5.3, and this is part two of the fundamental theorem of calculus. This is the part that we use the most. Okay, so that's why we're going to this next. The idea is that the Riemann sum, the more and more and more of those rectangles you add, the limit as n approaches infinity of that sum produces what's called a definite integral. Okay, now we can put the bounds, remember the a and the b before, where we start our rectangle, where we stop our rectangles. All we have to do to truly evaluate an area under a function is find an antiderivative. Remember, going from lowercase f to capital F. All right, you find an antiderivative. All right, and then you just plug in your two bounds. All right, you plug in b, and then you plug in a, the left bound and the right bound, and then the left bound, and then you subtract those two answers. It's incredibly easy. Okay, so let's do this. Okay, doing it is honestly just the way to go. So the first example we did this up here. Let's see. First example we did, it was 1/2 x plus 2. We were getting an area like 27. All right, we got to 28.5. We said we got to 27. All right, to do this with the fundamental theorem of calculus, we just have to have an antiderivative. All right, so we learned that you increase the power by 1. So 1/2 x squared. But then whatever this new power is, you divide by that new power. Okay, let me write this right. So the 1/2 x, we increase the power. Right now it's the first, so you increase by 1 to do an antiderivative, and then you divide by that new power. And then the 2 doesn't have an x, so it does in fact need an x. All right. Now the bounds, what we do with them is that we draw a vertical line right here, and you put the lower bound and the upper bound. Now we can simplify this a little bit. 1/2 times x squared over 2, that's x squared over 4 plus 2x, and we have our bounds from 2 to 8. All right, so to evaluate this definite integral, to truly find the area, what we do is we plug in 8. All right, so if I plug in 8, it would be 8 squared, that's 64. 64 divided by 4 is 16. Plus 2 times 8. All right, so 16 plus 16. I then maybe put that in parentheses. I then subtract. I plug in 2. Okay, so 2 squared. All right, 2 squared, that's 4. Over 4 is 1. 2 times 2 is 4. All right, so I add these two, 16 and 16, that's 32. I then subtract this sum, 1 and 4 is 5. 16 minus 5 is 27. The same answer we got before. All right, so let's try it again. This one, now square roots we have to remember are like x to the 1/2 power. So the antiderivative of that, I do x to the 3, 1 to that power, and then I divide by that power. The 4 gets an x. All right, it was a constant, so it gets an x. I then put this bound 1 to 9. Now, to divide by 3/2, what we can say is actually multiply by 2/3. And the 3/2 power is really the square root of x cubed. Okay. So I plug in 9. All right. I do 9 cubed. And then I take the square root. That's 27. 27 times 2/3 is 18. I do 4 times 9. That's 36. All All right, I then subtract my answer when I plug in 1. 1 cubed is 1, square root of 1 is 1. So here I have 2/3 plus 1 times 4 is 4. 18 plus 36 is what? 54 minus 4 and 2/3 would be what? 12, 14 thirds. And we get an answer of 49.3 repeating. Now, before, for the same problem in our second Riemann sum, we were getting an answer like 48.3, 47, 48. We had these little extra pieces left over. So the idea is that we are, in fact, getting very, very, very close. All right. So those are how we truly do the area under a curve. We just have to find an antiderivative and then plug in our two bounds. Subtract the answer after you plug in those two bounds. All right. So as you do these, try to make sure you kind of show your work just like I have. You don't have to show every work. Like I did a lot of that in my calculator, but I did write down some important pieces here. All right, so don't just do everything in your calculator. Don't just get a final answer for me. As you do these things, you have to make sure that you're showing some work. All right, so a couple more examples to make sure we have this. All right, so the integral, right, from 1 to 2 of x to the negative fourth. All right, so step 1, I have to find an antiderivative of x to the negative fourth. So I add 1 to the exponent, and then I divide by that new exponent, and then put my bounds from 1 to 2. All right, I can simplify this a little bit. This would technically be a negative exponent moves to the bottom. That negative 3 here is just, a negative number, so I technically have 1 over negative 3x cubed from 1 to 2. All right, so I can plug in 2. 2 cubed, that's 8. 8 times negative 3 is negative 24. I subtract, then I plug in 1. 1 cubed is 1 times negative 3. All right, so I have 1 over negative 24. I can do this in my head, never mind. To subtract those, what? I have to times by 8. All right, a minus and negative here would technically be a plus. So I've got 1 over 24, technically the negative should be on the top, plus 8 over 24. So 7/24 would be my answer. Negative 1 plus 8 is 7. All right, hopefully we are feeling good about that. Overall, these are not super difficult. Finding the antiderivatives, the hard part, plugging in those bounds, and then being able to just evaluate these things. So again, trying to show your work as you plug it in. Not a ton of work to show, all right? But we're showing something. All right, the hard part is that when you have things that are a little bit more difficult to find antiderivatives of. For instance, this is this times this. We don't have like a product rule for antiderivatives like we did for derivatives, okay? So the only way we can do these things is if we can find a way to just turn it into like a polynomial, all right, or a bunch of things being added or subtracted. We can't do it if these x's are being multiplied. So we do have to distribute this. So it'd be what? The square root of x plus, remember that's like the 1/2 power. So x to the 1/2 times x squared. We would add those exponents. It would be 2.5. So the 5/2 power. At this point, I'm going to go ahead and make that a 1/2. So again, the ln s here is our integral sign. We have our bounds from 0 to 9. The dx is just saying, hey, we are doing this with respect to x. X is the variable we're working with. All right, from there, we evaluate, or not evaluate, we do our antiderivative. I add 1 to our power, and then divide by that power. I add 1 to the power, so 5/2 plus 2, 5/2 plus 2/2, 2 over 2 is 1, would be 7/2 over 7/2, and my bound from 0 to 9. All right, I can make this look a little bit better. Instead of dividing by 3/2, I can multiply by 2/3 and make this back into a square root of x cubed. Here I can multiply by 2/7, and I've got the square root of x to the 7th. All right, so I plugged in 9. 9 cubed, the square root of 9 cubed is 27 times 2/3, 18, plus the square root of 9 to the 7th, yikes, times 2/7. So a wonderful, wonderful fraction. I think we can probably leave that as a decimal. 624.857. So I plugged in 9 first. Then I subtract. I plugged in 0. Well, that's really easy. 0 cubed is 0 times 2/3. That's 0. 0 to the 7th square root times 2/7. 0. So really my answer is just 18 plus this fun decimal. And I've got myself an answer. All right, so that's the big picture. Hopefully we can do these. These are just antiderivatives. Plug in your two bounds, and it finds the area. All right, that is the big picture of what we are doing for an integral. All right, using an antiderivative, and we're using this with what's called the fundamental theorem of calculus, part 2. All right, we'll talk about part 1 later. Not quite as useful for us, but it'll make sense once we get there. All right. Some other things that we just have to kind of know and be careful of is that you have to have a continuous interval. All right, and it has to be like the bounds have to be in the domain. Okay, so like this one, looks a lot like this one, right? But notice the bounds are just a little bit different. Now, if we tried to do it, we would get the same antiderivative, so it would be like x to the -3 over -3 from 0 to 2. Now, we can plug in the 2 just fine. That was 1 over -24. But when you plug in 0, you would get 1 over 0, all right? And we can't do that, okay? So you just have to be careful for what our bounds are. Also, let's just say this was like from -1 to 2. Now, the problem is in between -1 and 2 is 0, okay? And so the problem is, even if it's in between your two bounds, we can't do the integral if there's an undefined value somewhere in the middle, okay? The function has to be continuous on the interval. Now, if you're not sure what that means, not sure what that looks like, you can always try to graph the original function. All right, so you see how this function has this vertical asymptote here at 0. So we can't do the integral when it crosses over something weird like that vertical asymptote. The original problem we did was from 1 to 2. Notice how in that interval, the function's totally fine. It's continuous, and it's just this decreasing curved function here. But if you try to do this over the interval from like -1 to 1, or from -2 to 2, or from 0 to something, even at 0, that's where we have that vertical asymptote. It just won't work, okay? So you have to make sure that you check for any of those, domain issues before you try to evaluate your limits or your integrals. Now, we do figure out how to do some of these much, much later in Calculus 2. Okay, I'm talking like halfway through the Calculus 2 course do we finally figure out how to do some of these ones. So you just always have to double check that you are not trying to do the integral of something on an undefined bound. Okay, some extra information. The notation is from Leibniz, the co-founder of calculus. We've talked about him a couple times. All right, that elongated S, that long S to mean the word sum, and that dx, I hope you remember that, meaning that we're doing this with respect to the variable x, okay? We're not doing this with respect to y, we're not doing this with respect to t, or if the variable's t, we should have t's in here type of thing, okay? The a and the b are the the limits of integration, that's what we call them, through the bounds of x values. Okay, technically we call f of x the integrand as of the equation we're working with. All right, a couple more quick, easy ones. Hopefully quick and easy. All right, next up we have this one. Now, the problem that I notice is that this is two things multiplied together. We cannot do the integral of two things multiplied together. All right, we're just not there yet. We can't do that. But you know what we can do? We can distribute. All right, notice t is our variable and we have dt at the end. That's really good. So that'd be what? T squared minus 3t plus 2t minus 6. All right, so we have this new function. Now, are there any issues on our domain bounds? All right. Would this produce any issues? Well, no, that's just a quadratic. There are no domain issues in a quadratic. So we can do this. It's just a power rule. T cubed over 3 raised by 1 divided by that power minus t squared over 2 minus 6t. And then we put our bounds. Now, if you remember before, we used to do like the plus c at the end of our integrals. If you're wondering about that, we don't need to worry about that plus c. It would be a constant. Technically, if you plug in the 3, get an answer that has a plus c, and then subtract the answer after you plug in the minus 2 with the plus c, the c's would cancel out. I know that's a little too much. You're not worried about that right now. But yeah, we don't worry about the plus c when we have the bounds. We only worry about the plus c when you don't have bounds, all right? The indefinite integrals, all right? When we're actually finding areas, we don't need to worry about the plus c's. All right, but we plug in 3, all right? So 3 cubed, that would be 27 over 3, that's 9. 3 squared, that's 9 over 2. 3 times 6, negative 18. Notice how if there are 3 parts here, I usually try to write down 3 answers just to show, yes, I plugged that in there, in there. All right, I subtract. I plug in negative 2. Negative 2 cubed, that's negative 8 over 3. Negative 2 squared, that's positive 4 over 2, but it's minus, so minus 2. And negative 2 times negative 6 is positive 12. Here's where I would probably go ahead and evaluate this all at one time. All right, and we got ourselves an answer, negative 20.83. And then next up, a sine equation. All right, well, notice we have theta here, but d theta, that's good. We're doing respect to theta, and theta is the variable. I wouldn't, if I saw like a theta here, I need d theta here. If I had an x here, this should be dx here. Now, the bounds don't really matter when it's, when we're talking about the variables. These are just what we're doing our bounds on, our function. So we find the antiderivative of sine. Well, let's see. I know that the derivative of sine is cosine. The derivative of cosine is negative sine. And the derivative of negative cosine is positive sine. All right, so I know that cycle. So the antiderivative of sine would then be negative cosine. And we have our bounds from 0 to pi over 2. Now, sine, again, is a continuous function, always, so I don't need to worry about, any issues with our domain. So I then plug in pi over 2. Cosine at pi over 2 is 0, minus cosine at 0 is 1, the negative in front. So negative 0 minus negative 1, well, it's really 0 plus 1, and we've got 1. All right, so all of these integrals, as you're doing these ones, at least in the beginning of our course here, I guess end of our course right now, beginning of Calculus 2, they're all going to be very, very basic, Okay, we can't do integrals of composite functions, like the things that we needed the chain rule for with derivatives. When you have functions inside of functions, the complicated looking ones, we can't do those yet. All right, we can't do integrals of products. We have to like multiply them out, just like we did for these two. All right, we don't have rules for that, for products or for quotients. And then some of like the ones that don't simplify are that they're just more interesting. There's weird stuff going on. We're just gonna have to wait on those. They require some techniques that we need to just get the basics down before we get to those. Okay, so those are in later in Calculus 2. We might get to some of them. We will get to some of them here in Chapter 1. But the majority of the kind of interesting ones, beyond just the basic equations, they're for later on in Calculus 2, and we'll get to them. All right, eventually. Also, it's important to just kind of consider whether the areas in the problem should be positive or if they're allowed to be negative. Sometimes, depending on the context of the problem, you might need to just like change your answer from a negative to a positive. Usually, it would kind of discuss that, and we kind of know a little bit more about that. Actually, that is the next thing that we're going to talk about. So I'm actually going to stop this video right here, and that'll be the end of part 2 of our integrals video. All right, so forget what I was just talking about whether it should be positive or negative. We'll talk about that in a minute. But in general, I hope that we have a decent idea of how to evaluate integrals using the fundamental theorem of calculus.